degree was bestowed upon him in 2019. He is also an active consultant to many chemical industries. He is a life member of Indian Institute of Chemical Engineers and the Honorary Secretary of the Indian Society for Surface Science and Technology, Western Indian Chapter. He is on the editorial board of the Journal of Science and Technology India and has served on the editorial advisory board of the Industrial and Engineering Chemistry Research of the American Chemical Society. He also served on the CCC of the Advertising Standards Council in India. He has over 75 international publications and over 80 national international conference presentations and 10 patents to his credit. So let us welcome Professor Bhagwat. Sir, over to you now.
Thank you for the nice introduction. Can I use my presentation here now?
Yes, sir, you can start, sir.
Okay. Right, are you able to see my presentation now?
Yes, sir, it's visible, sir.
My screen with the title is visible to everybody?
Yes, sir, it's visible.
Okay. Good afternoon to you all. First of all, my apologies for the technical glitch. We delayed the talk by a few minutes. I'm going to talk today about interfacial science and engineering because there is both in it, science and engineering. So I'll talk about basics as well as the applications. The sections in the talk will be seen here. But before I begin with the talk itself, I'm going to tell you about where I come from. I come from this Institute of Chemical Technology in Mumbai. This was a place which was established back in 1933 by industries which, instead of the university wanting to start a department, it was the chemical industry in the western part of the country which desired to start such an institute. Today we have chemical engineering graduates, pharmacy graduates, and 7 different branches of chemical technology graduates. So about 250 people complete their graduation every year. About 100 to 150 complete their doctorate every year. Close to 300 complete their postgraduate degrees in various branches. We have almost 17 different branches in which students do post-graduation here, and about 29 different branches in which we publish a very large number of publications in the chemical engineering and technology area. In the NIRF ranking also we get ranked fairly high. While we do these publications, we also remember that we have to work with the industry, and it was a very surprising outcome when an IIM conducted a survey amongst chemical industry in India, asking them which is your go-to place to solve a problem. And 42% of chemical plus pharma industry together in the industry in the entire country voted for just one institute, which was ours. About 30% of our graduates end up becoming entrepreneurs, and today virtually who's who in the chemical industry is a graduate or a postgraduate or sometimes even both from the Institute of Chemical Technology here. We have several Padma awardees, including in our faculty, and the Confederate of Indian Industry, when it started an award along with AICT for Best Industry-Related Institute, not surprisingly, the Chemical Industry-Related Award came to the Institute of Chemical Technology consistently for consecutively 3 years. So that is the shoulders I get to stand on. So if I have some good work, it is a result of the background that I get to work with. So that is why I wanted to give you this background. So interfacial science depends on few forces which work in the fluid phase. Fluids, as we know, as different from solids, fluids will have molecules moving around freely. Solids will have locations of the molecules fixed. But these fluid molecules, when they are in the gas phase, they are so far away that they hardly interact. But when they are in the liquid phase, they have to interact. And the interaction between molecules in liquid phase is either because of the van der Waals forces, which are almost always attractive, or because of hydrogen bonding, which is present in some very unique solvents. In fact, this is one of the most important force in the most abundant solvent in nature, namely water. And many of the properties of water are different from other materials because of this hydrogen bonding. And the third type of forces are metallic bonds. I have arranged them in the increasing order of their magnitude. Compared to van der Waals forces, the hydrogen bonding as a force is easily 5 times stronger. And compared to hydrogen bonding, the metallic bonds is easily 10 times stronger. But obviously, metallic bonds are present only between those liquids which are metal. And liquid metals means either molten metal like molten iron, or liquid metals at room temperature, which would mean almost exclusively mercury. But the most common used solvent and the properties in which we are going to look at interfacial science in is water. And its very important component is hydrogen bonding. Molecules such as an octane or decane would be incapable of hydrogen bonding, because hydrogen bonding requires a proton donor and proton acceptor, and unless that is present, hydrogen bonding cannot take place. So for octane-like molecules, if I put them inside water, then the water molecules surrounding the octane will not get hydrogen bonding. The octane molecule desires only van der Waals forces, which it gets from the surrounding. But water molecules desire both van der Waals forces as well as hydrogen bonding. And if an octane molecule is present inside water, then the water molecules around it will not get the hydrogen bonding. And it is this that raises the free energy of the solution, and which in thermodynamics means the solubility of such molecules in water is therefore very restricted. Another commonly used term is the hydrophobicity or the hydrophobic effect. And what we must know, that we end up saying that a certain molecule is hydrophobic, whereas the property of hydrophobicity is not of that molecule at all. It is that strong desire that water molecules have to have the hydrogen bonding with each other. It is that desire that makes the octane molecule undesirable inside water. And that is what pushes out the octane molecule out of water. And it is no doing of the octane molecule really. But we end up saying that that molecule is hydrophobic, rather than saying that a water molecule is octane phobic. It is easier to talk about something being hydrophobic. So let us say, although grammatically hydrophobic means something which hates water, I will say hydrophobic actually means something that is hated by water. So the active side in the hydrophobicity is not the hydrophobic compound, but water molecule. Dr. Pillai, is the audibility and the sound as well having the slight clarity?
Yes, sir, it's clear, sir.
Okay, fine.
Yes, sir, it's clear.
Now, when
It's
we
clear.
talk
It's
about
visible,
molecules,
sir. Yeah.
thank you. Molecules like water are very strongly hydrogen bonded. In fact, the properties are substantially because of the hydrogen bonding. Otherwise, methane has a similar molecular weight like water, but methane boils at minus 150 something degrees Celsius, whereas water boils at plus 100 degrees Celsius. Such strong attractive force is provided by hydrogen bonding. But if I take a molecule which has hydrophobic part like I have shown here, and attach to it a very strongly hydrogen bonding part, and I have a chemically bonded polar part and a non-polar, non-hydrogen bonding part. Such a molecule has both properties, that something which makes it soluble in water, something which makes it soluble in oil. And such molecules have a dichotomy, and they do not know whether they should go inside water or they should go inside a hydrocarbon. And And when they find themselves inside water, then this part is still hated. This part is very much liked by water, but this part is still very much hated by water. And as a result, when I have water and in that I have put some molecules of this, the moment there are some molecules here, they see that there is a possibility that they can go to the surface of water and orient themselves in such a way that the hated tail is outside and the hydrogen bonding head group is inside water. When molecules come like this, then the free energy of this solution becomes less. So it becomes a preferred state. And in fact, there is an equilibrium between how much is the dissolved concentration and how much is this surface arrived concentration. This is called an adsorbed material and the phenomena is called adsorption. Obviously, we have an adsorption relationship between concentration of molecule here and the concentration of molecule at the surface. And at the surface, these head groups are actually quite big because of the bonded water around it. The head group is quite big and it doesn't allow another head group to come too close. The tail is relatively taking much smaller volume. So the tail becomes farther apart. In between there is air or water vapor, but this is liquid water which earlier was exposed to air. So these water molecules which are exposed to air were unhappy or having high free energy. Now those water molecules are hidden here and it is the surfactant molecule that takes the exposure to air. As a result, the free energy of this surface, which we measure as surface tension, becomes lower and the surface active agent, the name that we give to such molecules, comes from here, that at the surface they have a special activity and they reduce the surface tension of aqueous solution. But this is not the only thing that these molecules do. Normally, any solute, if I add in water, the properties of the solution change. One of them could be osmotic pressure. Osmotic pressure is a colligative property. So if I put more molecules in the solution, the property should increase. If I put sodium chloride in water, or if I put sugar in water, as the concentration increases, the osmotic pressure will keep on rising almost linearly till a fairly high concentration. Also, if I put sodium chloride in water, then the conductivity of that water keeps on rising linearly with the concentration of water, which means the equivalent conductivity, that the slope of this conductivity with concentration, is a constant. However, with these surfactant molecules, something peculiar is seen. The equivalent conductivity at a fairly small concentration of the surfactant suddenly starts dropping. And the osmotic pressure, which was rising linearly like any other solute, it stops rising. These two phenomena got scientists thinking about what must be happening that suddenly there is a change. They also noticed that the surface tension of the solution of a surface active agent is lower than that of water, and more the concentration of surfactant, lower is the surface tension. However, around the same concentration that these two phenomena happen, the surface tension reduction also stops, and any higher concentration of surfactant, we do not see any further reduction in surface tension. So scientists started thinking about what can be happening inside there which can explain all these observations. One thing was that osmotic pressure gave us a clue. That osmotic pressure is dependent not on the molecules dissolved, but on the species present in the solution. So if one molecule gives rise to one species, and every one molecule gives rise to one species, then of course the osmotic pressure should keep on rising linearly. But let us say, if 10 molecules give rise to one species, that means there is an aggregate formation, cluster formation, dimerization, trimerization. Then the osmotic pressure will not rise with the same slope. And here what we see is osmotic pressure was rising linearly like a molecular solution up to here, and then all of a sudden it almost stops rising. Actually, there is a very small slope here. And this concentration at which all these phenomena seem to be happening for a given surfactant at a given temperature, all these phenomena change at roughly the same concentration. And it is because of this that scientists proposed that these must be forming aggregates, and the aggregates must be large. Large aggregates would mean the number of species don't rise that rapidly. If the aggregation number is something like 100, then 100 molecules, instead of giving rise to 100 species, they would give rise to only one species. So therefore, osmotic pressure we will feel is almost not rising. And such a cluster will have to be of a very peculiar nature, because equivalent conductivity is also dropping and surface tension is falling. Now surface tension stops because there is no further molecular solution in the solvent that is present. That means up till here, whatever molecules I added, they were forming a molecular solution. But beyond this concentration, whatever surfactant molecule I add to the solution, they form clusters. Now, what are these clusters? The proposal for the clusters was like this, that the clusters will be of such a nature that this is three-dimensional structure. Imagine like a football, and the football surface has those hexagons. That is what these head groups are. And these head groups, therefore, come in contact with surrounding water. And their tail groups, which were hated by water, they all come together inside and they are protected from being exposed to water. So no longer are the water molecules hating them, because they have formed their own ghetto here, and what water sees is only the surrounding surface, which is of hydrogen bonding polar head groups. Such a cluster is called Micelle, and the aggregation number of these clusters is typically more than 20, 30, sometimes even in hundreds. And as a result, when an ionic surfactant is put into the solution, and let's say one molecule generated 2 ions and the conductivity was rising, if a cluster forms like this, let's say 100 molecules form a cluster, then those 100 molecules without cluster were giving 200 ions. With cluster, at best they can give one large ion, which is so big and sluggish that it cannot conduct, and only 100 ions can be formed. Not only that, if this 100 strong charged ion is present in the solution, it will capture many of those other ions. Those other ions are called counter ions. And the counter ions also get captured by this to some extent. And as a result, out of 100 molecules being put into the solution, I get one cluster, maybe about 50-60 counter ions also captured. So only about 20-30 ions or maybe 40 ions are formed instead of 200 ions. So naturally, the conductivity, which was linearly rising, suddenly changes slope. Slope change means the equivalent conductivity drops. That is how scientists concluded about this cluster formation. And they also realized that this happens only beyond a certain concentration. Below that concentration, micelles don't form. But what if there is a surfactant molecule whose solubility is very low? Because surfactant has the hydrophobic part also. If the surfactant solubility is very low, then it will not reach the concentration required for forming micelles at all. That is a very peculiar phenomenon which happens. I will explain that shortly. But here, what I am showing on this slide is that the aggregates are not always spherical. Some molecules, some surfactants form ellipsoidal or large cylindrical rod-shaped micelles as well. Some form double-layered structures which are called vesicles. Some form bilayers which are very extended, and some even form micelle-like structures, but in hydrocarbon solvent, these surfactants are not even soluble in water and they form reverse micelles. To form these different structures, there are two things which you should know. One, I have shown the molecular type, and one, I have shown a formula here. The formula is volume of the chain, length of the chain, and the area that the head group requires, within which it doesn't allow another head group to come on the micelle surface. This parameter is called the packing parameter, and geometry will dictate that if this parameter is less than 1/3, only then it can form a sphere. If the parameter is greater than 1/3 but less than half, then varying lengths of cylinder will get formed as a cluster. And this parameter will be greater than 1/3 to 0.5 if the molecule is such that compared to the chain, the head group doesn't occupy much area. Especially if it is an ionic head group, the ionic repulsion makes the head group area much larger. Non-ionic head groups are typically smaller. Then, going on further, if this packing parameter becomes greater than 0.5, then even cylindrical structures cannot be formed. We will see what is the geometry of that. But they form vesicles. Typically, if I have one head group attached to two tails, then such molecules will have packing parameter greater than 0.5, less than 1, and they will form vesicles. If I have small head group and two chains, then it is likely that it will form bilayers which are extended, not clusters which are closed, but extended bilayers. And if I have two chains, they also have a side chain and a single head group, then these are likely to have the packing parameter greater than 1 and therefore likely to form reverse micelles. So these are all different structures which can form. But come back to the question that I had asked, what if the solubility of the surfactant is low and it does not reach the minimum concentration required for forming micelles? In that situation, this line is representing that situation, and in that situation, if I try to dissolve a surfactant there, it will dissolve only up to the solubility limit. Beyond that, it will not dissolve at all. So it will form chunks suspended in water. So if I take a surfactant for washing my clothes and the solubility of the surfactant is low, instead of washing my clothes will actually become dirtier. But we know that solubility rises with temperature. So maybe there is a certain temperature beyond which the solubility becomes more than the minimum required concentration for forming micelles. And once that solubility limit is the solubility crosses the limit of that micelle formation concentration, now any additional surfactant molecule that I may add, it doesn't have to form solution in the molecular form. It will form clusters. And these clusters are completely hydrogen bond loving, because on the outside, it is only hydrogen bond capable head group. And any number of such clusters in water become acceptable. They will not be repelled by water at all. So as a result, any number of such clusters can dissolve. Any number of molecules that I add will keep forming clusters, and the solubility which I am measuring by putting in surfactant in the solution, I will feel the solubility has shot through the roof. That means the solubility up to this temperature was very low, maybe rising very, very slowly. But at this temperature, all of a sudden, the solubility seems to have shot up several hundred-fold. This surfactant which I have shown over here is sodium dodecyl sulfate. And at temperatures typically below 810 degrees Celsius, its solubility is below the CMC. And above that temperature, solubility is above CMC, and therefore the apparent solubility, not of the molecule, but of the molecule plus the micelles, becomes actually several hundred millimoles per liter. Here, it is just about 5 to 10 millimoles per liter. Here, it becomes several hundred or even 1,000 millimoles per liter can dissolve. This temperature at which it crosses the CMC is called the Krafft point. And it is a very important property for many applications. As I mentioned, if I am washing clothes, I better have a temperature of my surrounding above this, otherwise my clothes washing will be meaningless. And if I live in a country where the temperature is 5 or 8 degrees Celsius, then I might as well have a washing machine which will heat the water to beyond this temperature. Of course, it is possible to put some additives and reduce this temperature for surfactants, but otherwise I will have to have hot water wash. Fortunately, in our country, temperature is always above typical clothes washing surfactants Krafft Point, and therefore we don't have to worry. Now here is a diagram about the geometry I was talking about. You can see this is the spherical structure drawn in 2 dimensions with R as the radius. It should be only up to here really. This sigma or A is the area that head group requires before it can allow another head group near it. Now a sphere has a volume 4/3 pi r cube and a surface area 4 pi r squared. And if the sphere is formed entirely out of the hydrocarbon chains and the chain has a volume Vc and the aggregation number is n, then n times Vc must be equal to 4/3 pi r cube, and the entire surface of the sphere is made up of the head groups, so n times sigma must be 4 pi r squared. And when I take a ratio of these two, I'll get r by 3 equal to Vc by sigma, and I must also remember that this r can be smaller than the length of the chain, but it cannot be larger than the length of the chain. So there is an upper limit on r for a spherical micelle. Because if the radius becomes larger than the length of the chain, at the center there will be either water or vacuum. If there is vacuum, it will suck the molecules inside. It will not stay. And if it is water, then water will be heating the surfactant tails which are around it. So water will not want to stay there, water will want to go out. So spherical micelle can only be formed with radius less than LC. And that means this Vc upon sigma and that LC here becomes that packing parameter. And if that is Vc upon R sigma is equal to 1/3 or Vc upon LC sigma is less than 1/3 becomes the criterion for spherical micelle. On the other hand, if the Vc upon LC sigma is greater than 1/3, then the entire volume of this cylindrical region has 2 hemispheres and a cylinder. So this is the cylinder's area, this is the 2 hemispheres area, volume, and this is the area. So once again I can take the ratio and I will see that in the limit that the end hemispheres are negligible, I will have only cylinder, and in the cylinder ratio, when I look at that, I will get Vc upon LC sigma equal to 0.5. So 0.3 and less gets me sphere, greater than that gets me a cylinder with hemispheres, and if it is equal to 0.5, I will get cylinders of infinite length. Such cylinders of infinite length are like polymers, and they in fact give very high viscosity and also viscoelasticity to the solution. Many properties exploit this property, this phenomena happening inside the micellar solutions. Here I have shown that in an emulsion droplet where there is an oil drop and there is surfactant around it, this is the length of the chain and this is the diameter of the droplet. Typically, the diameter of a droplet is several microns and length of the chain is typically 1-2 nanometers. So there is at least 1,000-fold difference in the diameter of a emulsion drop and the surfactant chain length. Whereas in the case of micelle, the entire diameter is equal to twice the chain length. Twice the chain length would mean it will be about 2 or 3 nanometers only that will form the diameter of such a sphere. This is a diagram of a vesicle, that bilayer structure which I was talking about, spherical or circular bilayers. This is the diagram. Head group, 2 tails, another 2 tails surfactant, and its head group on the inside. So tails are touching tails, no water here. Head groups are touching water on the surrounding, and there can be water in the core as well. Such structures look more and more like a cell. This is like a cell wall. This is the interior cell fluid, and this is the exterior. Just give me a second. And such structures, therefore, are often used as substitutes for cell, and pharmacy people calls these vesicles by a different name. They call them liposomes. So liposomes or liposomes are same as vesicles, and they form when the packing parameter is beyond 0.5 but less than 1. If you have any questions, you can interrupt me at this point, because I am going to now talk about the chemistry of surfactants a little bit and some of the applications. Dr. Pillai, you would prefer some questions to be taken at this stage?
So, you can have questions even now.
I'm not able to hear you properly. You can put a question.
You can write down in the chat box.
In the chat box, if you write down questions, I can take them at the end also. That's a good idea.
Yes, sir.
Okay, so let me go ahead. Surfactants will have a tail and will have a head group. So the tail can be hydrocarbon or fluorohydrocarbon. Tail can be branched or it can be straight. It can contain aromatic group or without aromatic group. And the chain group can come from petroleum or it can come from vegetable oil. Depending on that, all of these are given different names. Head groups, on the other hand, their classification is either ionic or not ionic. In the not ionic type, it might be classified on the basis of origin. Some of them are called natural ones, sugar-based, sorbitol-based, they are natural, or petroleum-based, which is typically ethylene oxide derived. Non-ionic surfactants are also classified based on solubility. When the solubility in water is low, we say the HLB is low and they are oil-soluble surfactants. When the HLB is high, they are water-soluble surfactants. Amongst ionic surfactants, they can have either a positive charge on the surfactant ion and the counter ion is negative, that is called cationic surfactant, or the surfactant ion is negative and the counter ion is positive, it is called anionic surfactants. And there are some peculiar surfactants which are zwitterionic. Depending on pH, they can become cationic or anionic or even non-ionic. So we'll come to those type of structures. I'm going to show some structures here. This is an anionic surfactant shown with a 12 carbon chain here, carbon oxygen bond here, sulfur O, 3 O's and Na. So this will ionize at this O-Na bond, O minus and Na plus. So this part of the molecule, which is the surfactant part of the molecule, has a negative charge and therefore it is an anionic surfactant. And Na plus becomes the counter ion. Note that there is a carbon oxygen sulfur bond here. Here I have shown a petroleum based anionic, which is chain, alkyl chain with a double bond. I have shown carbon sulfur bond and 3 oxygens and O minus metal plus can be sodium. This will also ionize as an anionic surfactant. Cation will be the counter ion. This is called a sulfonate with a carbon sulfur bond. This is called a sulfate with an oxygen sulfur bond. The carbon sulfur bond has an oxygen in between. It's called a sulfate. Without that, we call it a sulfonate. Here I have shown a petroleum based chain with branching. Here is an aromatic ring shown here and 8, 10, 12 carbon chain attached to it and sulfonate and again an anionic surfactant and cationic counter ion. This is called sodium alkyl benzene sulfonate, and the most commonly used one is with linear chain. So the linear alkyl benzene sulfonate or LABS, or in the sulfonic acid form it is called LABSA, LABSA, is the most commonly used workhorse detergent for clothes washing. So this is that surfactant which is used in clothes washing. Then here I have shown a surfactant which is very, very simple. This is a hydrocarbon chain with a double bond here. Typically, this is an oleochemical and a fatty acid group here. And oil is a triglyceride, so glycerol and 3 fatty acids. When you hydrolyze, you get the fatty acid. And that itself, I have shown it as a surfactant. Only thing is, it is in this form, it is not very surface active. But if I make the pH alkaline, this will become COO minus and Na plus, and then it becomes an anionic, very good surfactant. And these carboxylate surfactants are given a particular name in common usage, and those are called soaps. Whereas the synthetic surfactant, which have a lot of synthetic group here, because this is benzene with alkylation done with a linear alkyl group, will be called the detergent alkylate, and then sulfonated. This kind of material, which has a lot of synthetic thing in it, is typically called a detergent. The word detergent actually comes from its action, that is detergency. Detergency is the way in which it removes dirt from clothing. So the word detergent typically is used for such synthetic materials which are used for detergency, and the word soap is used for such carboxylate material which is typically used on skin. The soaps that we use are typically carboxylates. They are much safer on skin than this material. This is much stronger, much better cleaner, but also rough on your skin. So this is never used for skin, this is used for clothes. This can also wash clothes, but this will be more efficient at washing clothes. And also this will be more expensive than the petroleum derived one. So that is why this gets used for skin, this gets used for clothes. I have shown over here a peculiar surfactant which has 2 chains with a side chain and an ionic head group. This molecule will form reverse micelles. Its packing parameter will be greater than 1. This will not dissolve in water, it will dissolve in oil. The molecule name over here will be sodium di, because of the 2, di-2-ethyl hexyl, because this is dioctyl but with a side chain. So di-2-ethyl hexyl sulfosuccinate. This is the succinic acid. So di-2-ethyl hexyl sulfosuccinate sodium salt. Too big a name. So typically many of these surfactants end up having a trade name, and this is typically called AOT or aerosol OT, which means sodium salt of di-2-ethyl hexyl sulfosuccinate. So this is the carboxylate typical soap. Now I have shown here a cationic molecule, a chain with a quaternary ammonium group here. So N will ionize as N plus and Cl minus. The counter ion is with a negative charge. Most common cationics are with quaternary ammonium compounds, and in fact they have a special property because of being quaternary ammonium compounds, that they are antimicrobial. So they are used as antiseptic material, antimicrobial materials in many applications, and obviously their price is higher because of this application. So nobody will use this for washing clothes because it will be very expensive. Not only because it has a better application, but also because typically this is a fatty chain. Fatty means fat derived. Fat means vegetable oil. So fatty acid is made into this amine. Typically fatty acid will be converted to fatty alcohol to fatty amine. Then you do the quaternization and then you get this molecule. More the steps, more is the cost involved. Whereas when you talk about lauryl sulfate, this is fatty acid converted to fatty alcohol, then sulfation, then neutralization. Relatively less costly. Whereas this, the fatty acid sodium salt itself, or this what is shown here, will be much cheaper to make, not much of synthetic intervention. So this is much more a natural molecule than this molecule, although the starting chain part is coming from similar source. Okay. Now here I have shown that zwitterionic molecule. It has a tail. It has an amide linkage. Then again 3 carbon atoms. Then there is a quaternary ammonium group. And after the quaternary ammonium group, there is CH2COO minus, which means this is an acetic acid kind of a group. This molecule is called a betaine. This is actually lauryl amidopropyl betaine. So amido means this amidic group, propyl means this C3, and betaine talks about this particular combined structure over here. So this is lauryl amidopropyl betaine. But even the lauryl chain is rarely obtained purely as C12. From natural source, when vegetable oil is hydrolyzed, you get molecules of 12, 14, 16, such kind of chain lengths. And therefore, you will have that mixture present. And many times this will be called a cocoamidopropyl betaine, CAPB, meaning this is the coconut oil hydrolyzed fatty acid, whatever is the mixture. So, we'll also talk about sodium cocyl sulfate instead of lauryl sulfate or dodecyl sulfate. Coconut oil has primarily or majorly C12 fatty acid. So therefore, when you derive it out of coconut oil, you will get major part will be C12. So sometimes people will call it lauryl, sometimes they will even call it cocyl. So for this, both words are used, lauramidopropyl betaine or cocoamidopropyl betaine, meaning it is derived from coconut oil. So obviously there is a substantial synthetic part, but combined with a natural part. Such molecules are called natural derived molecules. On the other hand, I have shown over here a fatty acid attached to sorbitol, which is a sugar. So this gives it a lot of hydrophilicity and this gives the hydrophobicity. So this surfactant is both parts natural. So this is called a natural surfactant. Not a biosurfactant, but natural formed surfactant. From natural groups, I have formed this surfactant. This is semi-synthetic because I have taken a fatty alcohol and I have reacted with ethylene oxides, and this ethoxylates is what gives the hydrophilicity. I may do a combination of this. I may have this along with ethylene oxide groups in between. Both this molecule and this molecule are commonly used in food additions. In many of the foods like biscuits, breads, they use these kind of surfactants, and the chain is either called span or tween, or even just the glycerol attached to this single chain, GMO, GML, glycerol monolauride. These are all food type surfactants. Now here is another type of mixed surfactant, which is a fatty alcohol ethoxylated and then sulfated, because ethoxylation also gives OH group at the end. I can do sulfation of that. So this is sodium lauryl ether sulfate as against sodium lauryl sulfate. This is sodium lauryl ether sulfate, and this molecule is one of the mainstay molecules for all shampoos that you might be using. Sodium lauryl sulfate, on the other hand, is used in toothpastes. Our buccal cavity is much stronger. Our skin or head skin requires a milder surfactant. So instead of lauryl sulfate, we use lauryl ether sulfate. Buccal cavity is much stronger. Therefore, we will use a stronger and better surfactant, which is lauryl sulfate. Skin, on the other hand, cannot take lauryl sulfate also. So therefore, we will use carboxylate. So the chemistry determines many of these applications. Yeah, let me look at some of these questions here. Water is a mixture of hydrogen and oxygen. No, it is incorrect. Water is a compound of hydrogen and oxygen. There is a huge difference between saying it is a mixture of hydrogen and oxygen and a compound of hydrogen and oxygen. Why can't we prepare water in the lab? Oh, most certainly you can. If you just take a hydrogen and oxygen and mix it, it will not remain happy just mixing. It will explosively react and form water. So I don't know what you mean by saying that you can't prepare water in the lab. You can, but please don't try. It is an explosive reaction. Hydrogen coming in contact with oxygen can lead to an explosion. But yes, it can be formed in the lab. In fact, anything that you burn, it starts with a fuel which has hydrogen as well as carbon in it. So when it burns with oxygen, it gives rise to H2O and CO2. So that's formation of water. So formation of water in the lab is indeed possible. Can the surface tension of water be greater than 72, like 76? Yes. If you take a molecule which will not want to go to the surface, it will want to stay away from the surface. This is said to have a negative surface excess. Such solutions will have a higher surface tension than water. Typically, molecules like sodium chloride will do that, but it will rarely go beyond 75, 76, and that too with fairly high concentration of salt. So such material will not form a micelle, and therefore there is no question of determining CMC of such solutions. It is only surface tension reduction that will be caused by surface active agents, because they are actively preferred to go to the surface, and which means surface tension will be reduced. So determining CMC is through the reduced surface tension. Okay. The next question is petroleum based. There are two types of structure, aromatic and branch. So are these petroleum used at petrol pumps, or it is used in any other way? Okay. When you say petroleum based, it is talking about petroleum crude oil based. Now crude oil is a combination of thousands literally of different types of molecules, aromatic, non-aromatic, and many different types. And which means when you take that petroleum crude, you have to separate it. In a refinery, crude oil is distilled into several parts. One of them is naphtha. One of them is a cut which is called light oil, heavy oil, gas oil. All these terms are there. What we see in the petrol pump is only two parts particularly of this. One is the gasoline part, which we in India call petrol, and the diesel part. Yet another important component is kerosene. All these come under the classification of petroleum. So branch or aromatic, they are all petroleum crude oil derived. Naphtha gives rise to benzene, toluene, xylene, and then you make derivatives of that. So that is all petroleum derived. One last question before I go ahead. Can the HLB value for long chain ionic liquids be calculated? Now when you talk about ionic liquids, they hardly have any hydrophobic part. And the entire HLB scale was defined only for non-ionic compounds. It has been extended to some of the ionic surfactants, but it does not conform to the primary definition of HLB. HLB definition was what weight percent is hydrophilic, what weight percent is hydrophobic. So you take the hydrophilic part weight percent and divide it by 5. That is what is called HLB. HLB is simply weight percent of the hydrophilic part divided by 5 of a non-ionic molecule. So ionic surfactant HLB itself is relatively imaginary. So ionic liquids, unless they have a tail, they are not even surface active. So even there HLB will be a notional value only. So it cannot be calculated from the structure. Something has happened with the presentation. Ma'am, shall I go back to presenting?
Yes, sir. We can see your screen.
My screen is visible? Okay. I thought
yes,
somebody
sir.
by mistake put some other screen. Okay, you can see my screen, then I'll continue. Okay.
Yes, sir. We can see.
Now these all surfactant molecules, when they adsorb and when they form micelles, they give rise to very peculiar properties and therefore applications. So properties such as when I put them in a solution, normally when I put an oil drop on water, it can either spread like this or form a blob like this. Vegetable oil typically will form a blob. Kerosene will typically spread. And what it will do depends on this relative play of surface and interfacial tension. But I can add a surfactant and make a spread oil go like this. I'll show a slide later on for that. Then there is this phenomena called contact angle. When I put a solution liquid on a solid surface, the drop can be either like this, or it can be very flat, or it can be nearly spherical like a mercury or water on a lotus leaf or water on most leaves. It will form nearly spherical drops. That angle here inside the liquid is called the contact angle. When the contact angle is low, we say it is a wetting liquid. And it is high, I say it is a non-wetting liquid. Both have applications. For example, when I am painting a surface, I want the contact angle to be low so that the paint goes everywhere and forms a uniform coat. And when I am doing cooking at home, I want a non-stick material made of Teflon where water will have a very large contact angle and it will therefore not stick. Other side of the story, when I want something to stick, when I want adhesion, I want very low contact angle. So all these are related to the property of contact angle, which is a result of three forces acting on this drop. One is the solid surface wanting to expose itself to vapor. One is the solid surface wanting to be covered by liquid. And second thing is the liquid not wanting or wanting an exposure to vapor. But that liquid vapor surface tension acts at an angle. So if you take the cos theta, then it becomes in this direction. So solid liquid surface tension plus the liquid vapor surface tension times cos theta act in this direction. And the solid's tendency to want to be exposed to vapor, which I have called solid vapor surface tension, acts in this direction. And it is this force balance that decides whether the drop will be nearly flat or nearly spherical or somewhere in between, like I have shown. That force balance equation is called Young-Dupré equation, and many applications are dependent on this. When I am washing clothes, I want the water to penetrate everywhere, so I want a low contact angle. When I am spraying a pesticide on the leaf, I want a low contact angle. When I want to make a raincoat or a wind cheater, I want it such that water will simply roll off. If I am a duck, I want my back to not wet when I am going inside water. So the ducks secrete a liquid to make the contact angle of water very high. In fact, when man learned from the duck and made a raincoat, one of the most famous brands of raincoat, maybe 50 years back, I don't know if it's still popular today, was the duck back raincoat. Because it mimics the duck's back, which doesn't get wet if I pour water on it. Water off a duck's back or something like that, terms also come like that. Or even there are many leaves. Famously, there are two leaves which are such that they give very high contact angle. One is a lotus leaf. If you put water on lotus, it will keep going here and there and it will be rolling as spherical drops. And the second such molecule is, I don't know what it is called in Hindi or Gujarati, or even in English for that matter. In Marathi, it is called Aru. Anybody can tell me what it is called in Gujarati? In fact, there is a saying in most Indian languages, like if you try to teach somebody who doesn't want to learn or is incapable of learning, it is like water off a duck's back. In Indian languages, the kahavat is about this leaf. In Marathi, we say alva varsa pani. Alu means that leaf, and on that water will not, it will simply roll off. It will not wet that leaf. That is because the contact angle is high. What is the name of that vegetable which has that leaf? Anybody knows? No? Okay, let me go ahead. I'll show you some diagrams of this application also. Patra? Okay, maybe. Patra will. Fine. Yeah, learn something new. Thanks. This phenomenon of contact angle is also important for powder wetting, and you will say, why powder wetting? Now, if I make a tablet and when it goes inside my stomach, if it takes a long time for liquid to penetrate, it will not be a fast-acting tablet. Fast-acting tablets are all such that water will soak through very quickly, and that is because of the low contact angle. And measuring a contact angle on a normal surface is easier. With a microscope and a camera, I will be able to measure that angle. But for a powder, there is a very elaborate special technique that I require called washburn method to measure. I will not go into the detail of that, but for many applications, this is very relevant. If you recall your childhood materials, if you put Bonvita in milk, it disperses, but not very easily if it is cold milk or Horlicks or any such material. In cold milk, it doesn't disperse well, but in hot milk, it will disperse well. It is because there is a hydrophobic coating which dissolves in water, melts and dissolves in the milk part of it and makes it more dispersible. There are many applications of that kind for powder dispersion as well. In fact, the entire capillary action that we talk about is because of low contact angle with that material. If you take a capillary made of glass and put it in water, water rises in it. That is a capillary rise. But if you put the same capillary inside mercury, you will see that the mercury in the capillary is not at the level but below the level. So this is capillary depression. And that is because the glass has a low contact angle with water but high contact angle with mercury. If you take a Teflon tube or a typical plastic straw, it has a contact angle which is greater than 90 degrees Celsius. So if you dip it in water, water does not rise by capillary action, it goes lower. So many places such contact angle is an important phenomenon. Eleven, can you tell me in the audience how many are students and how many are faculty members or scientists?
Sir, around 60 students are there and around 40 faculty members are there.
Wow, that's a mix of both. So many of the things which I am explaining as if explaining to a student will be sounding too simplistic for many teachers. But bear with me.
Yeah. Actually, sir, it's very interesting and very engaging, sir.
Okay, fine, thank you.
Yes, sir.
In the applications, I am now having a slide about emulsions. Emulsions are two incompatible liquids brought together. And when I stir it, it forms the droplets. Now those droplets have a high interfacial tension. That means a high free energy. And we know in thermodynamics, anything that reduces free energy is a preferred thing. So when two droplets like that come close together and they merge forming a single drop, the total surface area of exposure becomes less. And so therefore free energy reduces. So therefore emulsion droplets want to coalesce and become a single droplet. So if I want the coalescence to be prevented, I must reduce the interfacial tension, and which is what happens by adsorption of surfactant around the drops. And the stability of a formed emulsion depends on a few different things. Firstly, whether the emulsion will be fine or large droplet depends on, am I able to quickly reduce the interfacial tension? And then a formed emulsion will get destabilized by different mechanisms. I have listed three mechanisms here. One is called creaming. Formation of a cream in milk is because the fat droplets are light, they rise to the top. If the droplets are of a heavy material, they would have gone to bottom, but it is still called creaming. So that depends on density, the density difference, and also the creaming velocity will depend on viscosity of the surrounding. But a second phenomena, which is independent of density or viscosity, is Ostwald ripening. And that results out of an intricate equation of interfacial science called the Kelvin equation, which tells me that the solubility of a small drop is more than solubility of a large drop. And as a result, if I have a surrounding solution which is saturated, the question is saturated with respect to small drop or saturated with respect to large drop. If it is saturated with respect to large drop, then it is not yet saturated with respect to small drop. So the small drop will dissolve materially. But when it dissolves, the concentration here becomes more than saturated for this large drop. And the large drop will deposit some of the material onto it. And in due course, the small drop will keep becoming smaller and the large drop will keep becoming larger. This phenomena is called Ostwald ripening. This is present in foams, emulsions, solids, crystals, all of them. But that is something which you cannot really stop or even slow down. That will always be present in an emulsion. And third thing is, when emulsion droplets, let's say, cream up and they still remain separate, then if you just shake the emulsion, it will separate out the droplets. But if the two droplets merge to form a single droplet, then the wall is broken and the big droplet now will require a mechanical force to break. So just shaking will not separate it. So this wall breaking is the next step in destabilizing of an emulsion. So when you want to stabilize an emulsion, you have to counteract these destabilization phenomena. Or when you want to destabilize an emulsion which you did not want to happen, then you have to enhance these phenomena. Same thing actually applies to foams. Foams are dispersions of gas in liquid. Again, gas is non-hydrogen bonding. So water, which is hydrogen bonding, will have similar problems with gas. Formation of foam, when you are building a foam, if you quickly stabilize it, you get a fine foam. A fine foam has roughly the same thickness as a large foam. But as a result, a fine foam will be richer foam, because for same volume of bubble, I have this much of liquid around it. But if I have a large bubble and the same kind of wall thickness, the ratio of liquid to gas, liquid is much less. Rich foams are required in some applications. Say, for example, shaving foam needs to be a rich foam. But a detergency foam needs to be a open foam or a large bubble foam. Stability of the foam, on the other hand, is something else. The foam will have bubbles like this. In a foam, dispersed phase is air, continuous phase is water. But if you see the volume percentage of water is very low, volume percentage of the gas is higher. So the smaller volume percentage material is continuous and the larger volume percent material is dispersed. The stability again depends on the wall breaking, just like in the case of an emulsion. But the foamability and foam stability, which are two different words, foamability depends on the dynamics of how quickly is the surface tension reduced. Foam stability, on the other hand, depends on rupture of the wall. If the wall is pulled, does the surface tension go up drastically? These will decide foam stability. Microemulsions are some special types of emulsions whose droplet size, I'll show you the definition, is, sorry for skipping those slides. Microemulsions are droplets where they are less than 100 nanometers. And forming them does not require energy. Normally, forming emulsion requires energy. Forming microemulsion happens because of thermodynamics. Thermodynamically, it is favorable for the fine droplet to form. The droplet is of less than 100 nanometer size. Normally, an emulsion, it is unfavorable to form. If you keep an emulsion, it will separate out as in due course of time, but not microemulsion. Microemulsion has a thermodynamic driving force for formation of the drop. If you forcibly make two drops coalesce, they will automatically break up. So if you take the components of the microemulsion and keep them together without stirring, maybe overnight it will form a microemulsion. And because the droplet size is less than 100 nanometers, it is less than 1/4 the wavelength of visible light. Visible light is at least 400 nanometers. So if anything is less than 1/4 the wavelength of visible light, it does not obstruct the visible light. And if it does not obstruct visible light, you will think it is transparent. So in fact, it is difficult to judge between a solution and a microemulsion. Emulsion, on the other hand, is opaque because the droplets are large. Microemulsion are transparent. It is not only transparent, it is optically isotropic. That means in all directions, same properties. So the droplets are spherical. And many applications use microemulsions instead of emulsions. I will now launch into a series of applications, which at this stage, it is enough to just mention that these are applications. I can probably go on for an hour or so just on applications, but our time is limited as well as my biological limit of throat is approaching. So I'll go in this a little quickly. Applications of surfactants are wherever you need to bring hydrophobic and hydrophilic substances together. In paints, we have polymers and often dispersed in water. And we have particles like TiO2, which is going to hide the bottom surface which is painted. So all this dispersion is making incompatible things compatible. What can come in between is the politician molecule of surfactant. In many pharmaceuticals, the molecule is organic. It will be insoluble in water. But body is mainly water, 70% plus water. So you have to take it in an aqueous solution form. So to make the pharmaceutical molecule compatible with water, once again you use a lot of surfactants. There is an application in dyeing as well. I may have a slide about it. Fuel additives also, there will be a separate slide, so let me not mention it here. Food additives, you may not realize that biscuits, there is a lot of air inside. Use of surfactants, use of certain air bubbles inside it. Breads, when you form, there is a lot of dispersed gas inside, typically carbon dioxide. But how will it stay that way while the bread is getting baked? It is with the help of a surfactant. Cakes, when you make, those of you who have tried making a cake at home, a failed cake is like this, and a successful cake is like this from the same material. And that means there are air bubbles inside. Again, dispersing air there, you use surfactants which are not synthetic. Of course, there are food grade surfactants which you use. Yet another very interesting material where surfactant dispersing air is important is ice creams. The difference between kulfi and ice cream is very little. Main difference being there are very tiny air bubbles inside the ice cream. When you put ice cream spoon on your tongue, the taste is different than kulfi, and it is primarily because of the tasty material in it, but also because of the air bubbles breaking. That tingling feel that you get while you eat ice cream is because of those air bubbles breaking. And if the air bubble is not properly dispersed, ice cream will not be good. Pesticide, I will have a slide I will mention, and petroleum also I will have a specific slide. So I'm going to go through many applications and just barely mentioning why surfactant or interfacial science is relevant there. When you talk about pulp and paper, we are talking about recycling of paper. You want to de-ink the paper. Inks are made to adhere very closely to the paper. And waste paper to be recycled, ink removal requires that surfactant goes in between ink and paper and remove it. Normally, paper being made also, there is a good resin which is present in the matrix, which you want to remove to make the pulp. So obviously, you want to use surfactants there. And if the paper is such that it becomes hydrophobic, you cannot write with most pens. These days, you don't use so much fountain pens, but sketch pen, you will not be able to write on a plastic sheet. But on a paper, you can write. And that is related to the wetting phenomena or the contact angle. In metallurgy, there is something called froth flotation, that separation of mineral from the gangue material. You use tiny air bubbles which attach themselves to one of these two and they float. These materials then float because of the air bubble. Obviously, to create that kind of air bubbles, you are using surfactants there. That is called hydrometallurgy. In cold storage, if I don't spray certain liquids which will be going to the coal and making sure that the dust does not catch fire, then obviously there will be dust fires. To prevent that, I spray a liquid with surfactant in it such that the dusting does not happen. Leather, when it is made, the natural fat has to be removed. That is done by using certain surfactants. And synthetic fat has to be deposited. That is done by using a fat liquor material, which is again an emulsion of special type made with surfactants, which will allow that droplet of synthetic fat or synthetic oil to go inside the collagen matrix. When the collagen matrix is without such oil, and if it is dried, it will become powdery. Because of that oil going inside, you get the leather form. And once the leather is formed, it may last even for 100 years. But with the natural fat present inside collagen, the skin of an animal, once the animal is dead, the skin will start dying. So leather also uses a lot of surfactants. All the cosmetic formulations that we use, any creams or lotions, they are all emulsions. And to make emulsions, you obviously require surfactants. When you talk about inks, printing inks, let's talk about jet printing, inkjet printing. You talk about 600 dpi or 1200 dpi. That means such fine droplets should emerge from the nozzle. It should contain carbon particles dispersed in it. They should not block the nozzle. So again, you have to disperse them very fine, requires surfactant. That droplet which comes out needs to go to the paper and penetrate into the paper very quickly and dry out by the heat by the time it comes out. So that you will have 1200 dpi, 24 pages per minute, and the character should also be well formed. So pixels per inch. All that is dependent on the well-designed printing ink. Firefighting uses a lot of surfactants. Normally, for firefighting, you use water. But in a hydrocarbon, let's say in a petroleum company, there is a fire. If you put water on it, water goes to the bottom and the top hydrocarbon will keep burning. So what is done is it is not just water that is sprayed. It contains special types of surfactants which while spraying forms foam. Now foam is a combination of water and gas and that floats on the hydrocarbon. That cuts off the oxygen from air from the hydrocarbon which wants to burn and it will control the fire. Firefighting foams are a very special kind of foam. In civil engineering, when you are making a cement concrete, the cement particles, they have a friction. And to reduce that, you normally have more water so that it gets plasticity and you can apply it as a plaster. But more the water you put, more time it takes for drying and less is the final strength that it attains. So you want to do it with less water. But if you do it with less water, there is no plasticity and you cannot apply a plaster. So the solution to that is there are additives which are called superplasticizers or water reducing agents, which are basically surfactants, which adsorb onto the cement and sand particles, lubricate the surface so that the particle-particle movement is lubricated even with less water. And now with less water, the formed concrete is plastic, the plasticity is there, and yet it will gain a very good strength at the end. And it will be drying fast as well. So there is a lot of use of plasticizers, which are obviously surfactants in civil engineering. In electronics, when you are talking about something which is a silicon wafer and you are depositing something at a concentration of parts per million as a dopant, it means it cannot have any impurity in it at even parts per million or rather parts per billion level. Such level of cleaning uses a lot of surfactant. A typical silicon chip manufacturer uses several times its weight of surfactant in manufacturing it. In fact, something other also will be a very surprising use of surfactant when you see little later. In explosives, you want the fuel to be in very good contact with oxidizing agent. But if it is air, there is very little oxygen in air because gas is very dilute material. So normally the oxidizing agent is kept in a liquid form next to the hydrocarbon. But hydrocarbon is not water compatible. And the oxidizing agent is so therefore you have to make a very fine emulsion of the oxidizing agent with the hydrocarbon, and these are called plastic explosives or RDX. The research development explosives are all such specially formulated emulsions. Here is a coal anti-dusting shown here. This is the diagram of the coal cracks, and if I take just glycol and put it in it, it doesn't go everywhere. So it requires 200 strength for crushing it. But if I use the right kind of surfactant combination, you can see the strength required going down. When the strength goes down, it means it has penetrated well inside, and it will then lubricate the movement of the coal particles, and crushing strength required will be much less. In a coal thermal power plant, it is almost 5% of the power generated that is spent in crushing the coal. Coal is almost rock solid hard. And to crush it and make it into a powder for that combustion into the boiler requires a lot of energy. And that energy will get drastically reduced if you are using the right material to spray it. So it's not just anti-dusting for catching fire, but this is crushing power being reduced. Was that Tulsi Mukherjee sir that joined? Oh,
Yes,
welcome,
sir,
sir.
he has.
So glad to see you here. Okay, here I am talking about textile application. There are scoring applications. When I am making wool, there is a lot of wool grease because the sheep would have gone everywhere. So there will be a lot of oily material, there will be salts, and all that needs to be removed. That's called scoring. In cotton, scoring means removal of hemicellulose, some of the lignin, and some of the stray fibers. In synthetics, there are oligomers. All these come under the classification of what is called scoring. And these scoring agents, in fact, most of the textile auxiliaries use a lot of surfactants. And one of them I have mentioned over here are spin finishes. A spin finish is a coating on a fiber. Typically, in a textile factory, when you see there are spindles of fiber, and that goes through various processes, and there are 20 such houses through which the fiber will go before it is finally ready for making into a cloth. Now, this rate or the velocity at which this cloth is going is actually faster than a fast car. And when fiber goes at such a high speed over something, do you recall what happens when one fiber goes over the other fiber? During the month of January, I'm sure many of you had cases of one fiber rubbing against another fiber, and one guy shouts in victory that his fiber did not break, somebody else's fiber got cut. I'm talking about the shouts of Kaipoche. So basically, I'm talking about the kites and their strings rubbing against each other. Yes, patang. So the strings, when they rub against each other, they generate a lot of heat. Even at that kind of velocity, they generate heat and they break. So now, when I'm talking about in a textile factory, fiber going at faster than a fast car speed, it will generate a lot of heat and the fiber will break immediately. To prevent that from happening, what is done is that fiber is dipped inside a solution for a fraction of a second. And in that time, it picks up a surfactant coating on its surface, which then becomes a lubricant for that fiber going over a lot of those metallic parts. And now it does not generate heat. And at the end of that process, you have to remove that surfactant coating also, because the next house wants to maybe do mercerizing or whatever steps which are there. So it is again dipped in another solution, and extremely fast, milliseconds time, the fiber should remove the spin finish which it has got attached. They are given different names: coning oil, aeroning oil. They are all spin finishes. And the surprising part is, in a white shirt like this, during its life, I think I am using a lot of detergent to wash it. But in reality, the surfactant used in manufacture of this cloth, in the form of all these textile auxiliaries, is probably more than the surfactant I use during its life for washing. So surfactant is heavily used in textile manufacture, in fact more than what the laundering application that we know at home. Also, when you talk about softening, because when clothes are washed again and again, they become harsh, rough. So you use softeners. These are typically diquaternary ammonium, the two-tailed quaternary ammonium compounds. They also adsorb onto the cloth. They cannot be added to normal detergent itself. In the rinse cycle, you add those. that adsorbs onto the fiber, that lubricates the fiber movement, and it makes it soft. So these are also surfactants. In fact, when you talk about foaming and defoaming, you will be surprised to know that defoaming or anti-foaming agents are also surfactants only, which counter the action of one surfactant present in the solution. So many applications, without even realizing, they have surfactants. This is a fabric wetting. This is a dye solution dropped on a magnified cloth. If the dye is very badly formulated, it will form a blob on the cloth and it will not spread properly. If it will spread only in here, it will form only this part will get dyed and this part will not get dyed. What do you call such a print? Such blotchy print you sometimes deliberately want also. Normally you want a very uniform dyeing to happen so that it should penetrate and percolate through all the surfaces. But if it forms like this, which is an undesirable thing for a normal colored cloth, there is some specific application where you want such blotchy prints. They tie up a cloth and then do the dyeing process. What is it called? Women in the group will probably know more because such kind of clothing is more popularly used by women. Anybody? Go and look up. There is a very special type of fabric with blotchy print like that. But normally, dyeing you will require that the liquid should penetrate throughout. This is the normal household detergency application, which even is taught in school, that there is a dirt adhered to a cloth, surfactant comes, it penetrates, it lifts, it then keeps it inside this surfactant adsorbed layer and takes it away. So this is the detergency phenomenon. In pharmaceuticals, many of the drugs which are not water soluble are made water soluble, but at the same time, there are some drugs which, if they have too much water around it, they will degrade. So you want to protect them. So what is done is that they are kept in oil form, but in oil, those drug molecules will be very sensitive. So there is a tiny water coating around it, although dispersion is in oil and other way around also. And that is always attained by using surfactants. But a very interesting application which I have mentioned here is high oxygen carrying capacity substances. When you want to make something like a synthetic blood, you want it to have high oxygen carrying capacity. Oxygen solubility in water is very low, but that low solubility is what is responsible for our survival. Through that low solubility, it goes to hemoglobin. But just water by itself would not be sufficient for it. There are certain very specific microemulsions which are made, which can carry water as high as blood can. And then they can be used as a synthetic blood temporarily, still not used on human beings. Animal experiments are successful. Or there have been experiments where you make a submarine where there is no air supply and air is exchanged from surrounding water, the dissolved air, like fish do, through such liquids being put in a cycle. That is possible. But for that, you require very special types of microemulsions which are made with fluorohydrocarbons. So they are again using a lot of surfactants. In controlled release of drugs also, they use vesicles very commonly and also in targeted delivery. I had mentioned that vesicles look like cells. So if you have taken any medication and it goes into the blood, if it goes as a large drop, it will block the capillary. So if you are putting it as an injection and it's a large drop, that will be of no use. So you have to make a very, very fine emulsion of the size of the RBC, which is like the vesicle. And in fact, the vesicle wall looks like cell wall only. And there are some typical drugs where this is very necessary to do this to it, that these drug molecules should not get seen by rest of the body, except the part where the drug is supposed to act. A drug has a certain concentration which is minimum necessary, which is called the therapeutic limit, and an upper limit called the toxic limit. And targeted delivery makes sure that the rest of the body sees drug at less than toxic limit, but the targeted spot sees the drug at a higher concentration. And that is done through vesicles formed out of specific surfactants. This is an application in lubrication, and that is in lubricating oils. Lubricating oils require a certain pH to be maintained. But if I am having combustion of fuels, if CO2 and small amount of SO2, SO3 get absorbed, they will raise acidity. And to counter that, some of these will have extremely fine alkaline particles made through the microemulsion mechanism to counteract the SO2, SO3 absorb. The SO3, if it reacts with calcium carbonate, forms calcium sulfate, and CO2 is released, and the acidity is not formed. And that extends the life of the lubricant much more. In pesticide, here I have shown a photograph of a pesticide spray which is forming blobs. This pesticide is not going to be of any use. This will simply fall off from the leaf. This is a close-up. This drop is going to fall off from the leaf. Whereas here, I have sprayed it with a correctly formulated pesticide which is spreading properly and wetting the leaf. Whereas these drops are simply going to fall off, and the farmer will think that I have to put more pesticide. So more pesticide will reach your drinking water but not protect that leaf. Not only that, it might protect the weed which is below the leaf. So formulating the pesticide correctly, which will wet the leaf, will require good amount of and good type of surfactant. Not only that, these pesticides are sold as concentrates. The farmer pours the concentrated in water. He doesn't have an emulsion making equipment with him. It should spontaneously form an emulsion. Again, very specially designed surfactants for spontaneous emulsification. Third thing is, these emulsions are carried on the back of the farmer, and throughout the day farmer will be spraying it. So if the emulsion is not very stable, in the morning he will be spraying a concentrate, and in the evening he will be spraying only water. If you don't want that to happen, you want the emulsion to be stable over 24 or 48 hours. Again, very carefully prepared emulsion formulation. So in this agrochemical, the pesticide, there is multiple use of surfactant which is necessary. In petroleum recovery, it is water flooding and then surfactant flooding. What flooding does is water pushes out oil into the production well. But water cannot go in every pores. Some of the pores are hydrophobic. And that is where special types of microemulsion, bicontinuous microemulsions are used, that you put a bicontinuous microemulsion plug followed by water, and with that plug, which has a very low contact angle, it penetrates in all the rocks, and all the petroleum then will start getting pushed. This is used in what is called tertiary recovery of petroleum oil. This is the oil spill example I was talking about with the spreading property of the liquid. An oil which is fallen onto the ocean surface, it is going to spread. It will form a monolayer. And if I try to pump it out, I will be pumping out more seawater than the oil. So if I can force this liquid to form that blob, then I will benefit from it. And that is why that diagram which was there about the spreading coefficient, if I add the right kind of surfactant, very small amount at the edge here, this relative phenomena of what causes spreading and what causes blob formation changes. And what was spreading becomes blob forming. And the blob can be easily pumped out. So controlling oil spills requires the understanding of spreading of liquids over water. This is a very interesting application of fuels. And the title of the talk which I give with this is, Can Water Help Fuel Burn? Normally you will think water is for extinguishing fire. But we had used water to help burning in fuel. We made very fine droplets of water in oil. And what it did is, first of all, the half-filled can of kerosene, which normally has hydrocarbon and air, and it's a very dangerous situation that if there is a spark, it will explode. Here, with this water droplets present there, now I have water vapor as well as hydrocarbon vapor. And in the right combination, I make that non-explosive combination. And that makes the flash point become much higher and the fuel becomes safer. So it is a fire retardant fuel. At the same time, when the fuel comes to, let's say in a wick burner, fuel comes there, it actually makes sure that the rupture of the droplet causes better combustion. Think in terms of a primer star. The droplet of the fuel that comes there is at least 100 micron droplet. It gets heated to about 200 degrees Celsius and then it catches fire. And if it leaves the flame before it burns fully, it will leave soot. So if I make a smaller droplet, it will burn fully. But to make a smaller droplet, I have to apply a lot of pressure to that compressor. But that is only a hand cranked one. So I have a limitation. So if I have this kind of formulated kerosene and that comes as a drop there, it already has tiny water droplets, much smaller than the fuel droplet, water droplet, microemulsion droplets inside. Now, before the droplet of fuel becomes 200 degrees Celsius, the entire droplet will cross 100 degrees Celsius, and which means this tiny water droplet will boil. And when liquid boils, it becomes vapor. It requires much more volume. So as a result, this droplet of fuel bursts out into tiny fragments. And when it becomes smaller fragments, it has better surface area to unit volume, and then it burns fully to the core without leaving any soot. So this is a fire retardant fuel, but on the other hand, it helps fuel burn fully without any soot. There are many chemical reactions which you can conduct inside surfactant media. I am going to give only a couple of examples. First example I am giving is of preventing oxidation of vegetable oil. Normally, vegetable oil will become rancid. It will develop fatty acids by hydrolysis and the absorbance goes up. But if I put microemulsion of water in it, there is no difference. The second curve is also similar. But if I put this antioxidant in the microemulsion and then put it in oil, the absorbance is remaining constant. This antioxidant is not oil soluble. I could not have put it in oil just like that. But it does the job of preventing oxidation if it is put through a microemulsion. So that is preventing the oxidation of fats and protecting them. And here is an example of raising the rate of reaction. This is a molecule cyclododecanone. When I react it with hydroxylamine sulfate, it forms the corresponding oxime. This oxime undergoes Beckmann rearrangement and it becomes the amide linkage. The amide link can be polymerized into nylon molecule. So this is a commercially very important molecule. But this reaction is with a highly water-soluble molecule with a highly water-insoluble molecule. So if I conduct it in alcohol, I have another cost. If I do it in aqueous solution of this is a solid insoluble in water. If I powder the solid, the reaction becomes somewhat fast. But if I use the right kind of surfactant combination along with it, then even for the given powdered reactant cyclododecanone, there is a 600-fold increase in the reaction that you can see. Here is an example of selectivity. This is an example of chlorophenol formation. Phenol molecule can get chlorinated either at ortho position or para position. Normally, it is much more ortho position than para position. But if I put the surfactant inside and the phenol molecule goes like this, then the chlorinating agent can attack ortho but not the para. And as a result, I will get much more ortho than para. And in terms of application, when I chlorinate phenol, orthochlorophenol and parachlorophenol both are monochlorinated products. But if I do dichlorination and I get 2,6-dichlorophenol versus 2,4-dichlorophenol, this is a floor cleaning kind of material. This is, on the other hand, a drug and very expensive drug intermediate. Diclofenac sodium uses 2,6-dichlorophenol as an intermediate. So obviously, from the same starting material, if I can make more this than this, if I can change that selectivity, there is a huge profit in doing that. So this micellar method can be used for such molecules where ratio selectivity can be improved. So rate increase is possible, rate decrease is possible, selectivity is possible, and in some cases the selectivity can be not this orthopara kind of selectivity, but also selectivity of the kind which is this type. This is an example of making synthetic cocoa butter. Natural vegetable oil will have different fatty acids here. But to make cocoa butter, I require specific chain lengths. So if I take oil, remove this fatty acid, put the desired fatty acid, I'll get cocoa butter. But I cannot play Lego with that molecule like that. I have to use some catalyst so that this hydrolysis happens and the re-ester formation happens. That catalyst is a lipase. Lipase is an enzyme, but enzymes are active only in water. They are not oil soluble. I want this oil reaction to happen with that lipase. So I have to use a microemulsion to bring this enzyme molecule in contact with oil, and the enzyme molecule should be still protected inside water. This is the reverse micellar structure. And here I am showing that if it is anionic surfactant, I get the enzyme at the surface. With non-ionic surfactant, the enzyme doesn't go to the surface. So the right kind of surfactant is also required. But with the right kind of surfactant, I'll get the enzyme in contact with oil and I can make this kind of cocoa butter molecule. So I've mentioned this in very brief. There are not many intricacies to it. Even materials which are enzymes or proteins which need to be separated, that separation can be done by using reverse micelle to change the selectivity. But more on that you can read. Here I will only say that micelles can catalyze, they change selectivity, they can offer a physical protection of a group. When I am changing selectivity from para to ortho, I am actually protecting the para group. So that is called instead of chemical protection, deprotection, I am using a physical protection, deprotection. And to summarize, interfacial science has applications in many fields in the industry, but the fundamental principles which determine those applications, if they are studied, then everything falls in place. Common governing principles gives a better understanding of the phenomena which finally result in the application. Applications are in physical systems as well as in chemical systems, and characterizing the materials involved as surfactants and then using those properties to determine the applications. That is the key to work with these materials. I have a thank you slide for all the companies that have been associated with my research work over the last 30 plus years. There are some of them manufacture surfactants like Galaxy Surfactants. Some of them use surfactants to make consumer products like livers. Some of them use surfactant for textile-like applications like the Aditya Birla Group. Some of them into pharmaceutical products like Glaxo. Some of them in coal-related applications like Chemithon or Thermax. Some of them in personal care formulations like L'Oreal. Some of them for firefighting like KV Fire. There are many of them. So my thank you to all these companies to finance my research work over the years. And thank you to you all for very patient listening. I don't think I have left much time for questions, but if there are some, I will answer. Thank you for your patience.
Yes, sir. Thank you so much, Professor Bhagwat, for such a detailed and informative session. Now, I request all the participants to ask questions if they have. You can turn on your mic to ask your questions, or you can use a chat box for asking questions. Any questions, participants? If you have any questions, you can ask through chat box or through turning on your mic.
If some of them give you the question on email, subsequently also I'll try and answer those.
Sure, sir. Thank you. Thank you so much, sir. So I think the presentation was very detailed and informative, sir. So they are not left with any questions. So thank you so much once again, Professor Bhagwat, for such a detailed and informative session. I can already see from the participant messages that they found today's session very interesting and informative. I thank you once again on behalf of PP7 University and School of Sciences, and we invite you to join us at PP7 University when the things get normal and visit our universities.
Sure.
I would also like to thank our participants, and I'm glad that Dr. Tulsi Mukherjee sir joined us. It's an honor, sir, that you joined and blessed us by being a part of this webinar. Thank you so much once again. With this, let us end today's session.
Thank you.
Thank
Was
you,
there
sir.
some attendees from outside the university as well?
Yes, sir. There are many participants from outside universities, and only few of our students are there who have joined.
Okay. Any industry participants as well were there?
Uh, Few were there, sir. Few.
Okay. So thank you. Bye bye. I'll take
Yes,
you.
sir. Thank you. Thank you so much, sir. I request all the participants to kindly fill the feedback form.